is equal to, by the same argument we just went through, you know, sorry, I'm getting distracted by the stuff. I should just pushed on. This is equal to 1 again, so.
So W is the kernel.
Right, so if we let W equal that, so W equal to G, Z, G inverse is an element of the kernel of phi.
So Z.
And, okay, and then Z is equal to
G.
G inverse W, G.
Which is an element of G inverse kernel of phi.
Yeah. Sorry, these sort of onto arguments are sometimes a little slippery.
So what was different with that one from the one above?
So this shows that kernel of phi is a subset of the conjugate of the kernel of phi under G. But both of these arguments are true for arbitrary G. Consequently, kernel of phi is a normal subgroup.
One question.
Sure.
How do we know that phi of 1 is 1?
Oh, you can prove that. So like phi of 1 is phi of 1 times 1, because the identity times identity is identity again. So by homomorphism problem, that's phi of 1 times phi of 1.
Which means phi of 1 has to be the identity.
Oh, I see.
Because you could write 1 times this, and you have a cancellation property in the group, so I can multiply by phi of 1 inverse on both sides and get phi of 1 equals 1. Okay. Stick a fork in it. I think it's done. Sorry, I don't usually say that, but actually I was actually thinking I was teaching topology today. I brought a different book. I'm an idiot. I just I mean, I did have a chance to actually. I mean, I have read all of chapter 2. I know where we're going. It's just we're just taking our time getting there. Sorry about that. Now the beauty of cosets really is, I mean, the fact that it forms the fact that we've, okay, so you got the kernel phi as a normal subgroup, right? That means that you can factor by the kernel to a group homomorphism, and you get a well-defined factor group. And then there's this wonderful theorem, the first isomorphism theorem. It says this basically: if you've got a mapping, a homomorphism from say G1 to G2, then if you look at G1 mod the kernel of phi, which we know makes sense because kernel of phi is a normal subgroup, then this is in fact isomorphic to the image under phi of G1. So the domain mod the kernel is isomorphic to the range, or the image, if you will. So it's pretty neat, and there's a natural mapping from G1 to this coset space. It's just this. So you're like pi goes from G1 to G1 mod the kernel. The mapping is just this. Like you do pi of G is equal to G. Well, I want to say GH, where H is equal to the kernel of phi. But you could write kernel phi there if you wanted again. But. I mean, okay, to cut through the noise here, what we're really saying is that the kernel of phi in the quotient behaves like the zero, or it behaves like the identity. So when you mod by some normal subgroup, you're essentially taking everything in the normal subgroup and making it like it's the identity. So you're like just squashing everything in the larger group down, so you have a smaller group after you form the quotient. It's a lot like the idea we use with fractions all the time. You know, you've got a half, 3/6, 5/10, 20 40ths, 500 1,000ths, and so forth and so on. You can list all of these different representations of a half, right? But you just look at all of those things as that one thing we call a half. That's kind of the same sort of idea. Now, is there a question?
I don't know. I'm not really getting the significance of G mod kernel.
Oh, no, it will, right. I don't think it's gonna make, it's not gonna click why we're doing it until we get just a little bit further into the story here. So, bear with me here. Okay, so what I was trying to get to is the cosets to the group. The other nice thing about them is they basically partition the group into just disjoint subsets. The easiest thing geometrically to think about is an additive subgroup. Like, for example, the plane. You take any line through the origin, that's a subgroup.
Mm-hmm.
So you could basically, or you could even take R3. Here's a picture of R3, so to speak.
The infinite cube.
Yeah. And I could say H is like a vertical, like the plane through the origin, the XZ axis, basically the XZ plane, right? And if I do that, if I look at R3 mod H, what I actually have is basically isomorphic to R. See, because what I'm doing then is I'm taking these infinite planes, right, and I'm just squashing them to a point. Basically, I'm saying this whole plane is identified just by that point. It's, y.
Just by whatever point is on the y-axis that you're...
Right. I mean, that's a typical representative. I just need that label, the y there.
Yeah, the y is just there to make sure that you know which direction it's
But
coming from.
yeah, on the other hand, if you give me any point in R3, it lies on one of those planes and just one.
Right.
What's more interesting is for multiplicative groups, you pick a normal subgroup of a multiplicative group, the cosets which correspond to it can be weird stuff. For example, on page 26, he tells us that he shows some, if you look on page 26, he's got some pictures of these so-called Hopf vibration. What we're looking at is S3. Remember, what is S3? S3 is the
unit sphere in R4?
Right, the unit sphere in R4, the unit quaternions. This forms a group, and you can take a circle. There's a circle in there which you can prove is a normal subgroup, and its cosets give you these weird twisted circles when you look at. This is a visualization of them, as he says, projected stereographically. I mean, you can't visualize R4 directly,
Right.
but it's really interesting. Now, all right. One important homomorphism we have is the determinant, right? The determinant gives us a homomorphism from our matrix groups onto the set of non-zero complex numbers. Non-zero complex numbers form a multiplicative group, right? So the determinant's a homomorphism because the determinant of the product is the product of the determinants, and the determinant of the inverse is the inverse of the determinant, and what is the inverse in non-zero complex numbers? It's exactly the reciprocal function, so.
I thought I was thinking about isomorphisms, and I was like,
No.
the determinants are 1-to-1?
No, it's just the determinant homomorphism usually. The determinant will be isomorphism in some very special cases. All right. Then then this is the big idea that we will start to talk about today, but won't come to full grips with it yet. In fact, this is one of the really big ideas in this course. It's going to take us a while to some time to really wrap our mind around and properly understand is this notion of a simple group. All right. So he says this: a many-to-one homomorphism of a group G maps onto a group G prime that is quote-unquote simpler than G, or at least not more complicated than G. Nice. For this reason, groups that admit no such homomorphisms
The simple group.
are called simple. Yeah.
It's not a very good definition.
Equivalently, a non-trivial group is simple if it contains no normal subgroups other than itself in the trivial group. So it's much like the idea of reduced fractions.
What page is that?
This is I have made it green, as is my custom, on page 31, because it's the definition. But, so I mean, cut through the static, the idea of a simple group is that you cannot form interesting quotients in a simple group. There's no normal subgroups except for the whole group in itself. And so, like, what do I say, interesting quotients? I mean, if you take G and you factor by G, you get the stupid group. If you take G and you quotient by the identity, so what I'm saying is in this quotient, the identity has been identified with the identity, which is really just giving you a cumbersome notation for this again. Okay, so
there are no interesting subgroups? There are no interesting...
if there's no non-trivial, if there's no normal subgroups other than the identity and the group itself, in other words, if there are no proper normal subgroups, then you cannot make an interesting quotient.
So there are no non-trivial interesting normal subgroups.
Right. So this kind of simple group is, you know, that's what makes it a group is simple. You can't further divide. You can't break it down further by factoring. All right. So let me tell you where we're going without writing. Let me see if I can. All right, so next he goes on in section 2.3 to discuss the groups SU2 and SO3. So
what does U stand for in that?
right, let's talk about that. So I will stop at like 5:07 today. Is that okay? Okay, so remember we talked about the quaternions last time? And words. So H we looked at is this, is what particular kinds of 2x2 complex matrices, what do they look like?
They're A plus DI, negative B plus CI. Oh.
Yeah, go on.
A negative B plus CI, and then positive B minus CI, or is it plus CI?
I think it depends on which we put the minus on.
I think the bottom one is supposed to be positive B.
Yeah, you're right. You are right, sir.
Because they want, if C and D are 0, then it's just a complex, or then it's just yeah.
In the bottom right corner, it's a D.
Yeah, it's a D.
Oh, sorry. Yeah. All right. Now, so this was one way of modeling the quaternions, right? As a particular subset of 2x2 complex matrices. And S3 was what? So S3 was like, what, I mean, we could write it this way: Q, an element of H, right? Such that what? Determinant of Q is equal to 1. These are the so-called unit 3 sphere in R4. Right? I mean, these have a squared plus b squared plus c squared plus d squared equals to 1, right? In terms of the notation above. Now, if I look at Q as a 2x2 complex matrix, right? You can verify that it satisfies the following identity: Q conjugate transpose times Q is equal to what? Let's see here. Conjugate transpose. So conjugate does A minus DI, A plus DI. All right. The transpose flips the off diagonals, so I get like B plus CI up here because it's conjugate transpose. So I get down minus B plus CI down here. So what happens when you multiply this by
So all the conjugate did in the conjugate transpose was just switch entry 1 and 4, basically.
yeah.
Yeah.
A
That makes-
squared plus D squared.
Yeah.
And then this gives me that times that conjugate, so B squared plus C squared. Of course, we know that's 1, right? If Q is an element of S3, that is. Okay. And how about the 2-1 component? This times that, I get minus AB plus A plus CDI squared plus AB minus CDI squared, otherwise known as 0. Guess what? The same thing happens up here when you multiply it out. And you care to guess what the 2-2 component is?
7.
12.
When 7 is equal to 1.
It is.
It's gotta be 7.
Oh my goodness. Joe! Get out of here. Alright, so this is also A squared plus B squared plus C squared. It's 1 again.
Cool.
So a matrix which satisfies this identity, you could also write this as Q dagger Q. So this is the Hermitian conjugate, it's conjugate transpose. Q dagger Q equals to I once more. This is what's known as a unitary. This implies that U is an element of U2, as in my notation at least. I don't know, Stillwell probably talks about this sometimes, I don't know, maybe he already has, I don't think he has. So that's a unitary 2x2 matrix, and then the determinant of Q is 1, right? And since the determinant of Q is also equal to 1, in fact that implies that Q, sorry, I'd say U, I meant to say Q, sorry. Q is actually an element of SU2. So that's special unitary 2x2 matrices.
So again, what is the U?
Unitary.
Unitary. So it equals 1 basically, or the length equals 1.
Unitary, I think, has to do with, why is it called unitary? I mean, it's probability preserving. It keeps the probability 1 as this stuff intersects with quantum mechanics. Because, so like the probability, something like this, psi, and if you transform that to Q psi, the way this works is that's the same as psi, Q dagger Q psi. So the bracket of psi with psi being the probability that, has to stay 1. Anyway, there's a meaning for the term in quantum mechanics. I'm not sure. I don't know. I didn't think about where does the word unitary come from. I don't know. For me, it's born in quantum mechanics, but that's just why, I was raised by physicists. So, I mean, academically, but I love them. My parents are not physicists, but as far as I know. Okay. So S3 is naturally SU2 if we build the quaternions from this model. In fact, it's not like an identification or something. It really is SU2 in the current setup. So, all right. So as he says here, unitary matrices are the complex counterpart of orthogonal matrices. Now the reason for that is this is what so if you study the Hermitian, the sesquilinear, it's not bilinear, it's sesquilinear. It's like 1.5 times linear mapping from the Cn cross Cn to the complexes again. And if you look at the isometries of that inner product, the complex inner product, the unitary maps appear as the isometries of that complex inner product, in the same way that orthogonal transformations appear as isometries of the Euclidean inner product. That is in Tapp's book. All right, moving along here. So he says the group SU2 is closely related to the group SO3 of rotations, right? Because what do we start with? We started with looking at things in S3, and we showed how a pair of them, like that antipodal pair, produced the rotation by conjugation, multiplication by conjugation, in the unreal quaternions. So, as he says here, the group SU2 is closely related to the group SO3 of rotations. And then here's what he says. He says, we saw in section 1.5 that the rotations of R3 correspond 1-to-1 to pairs of antipodal unit quaternions. And then he reiterates the conjugation map. So, then what he's going to say here is you can have a mapping phi from SU2 to SO3, all right, defined by phi of t equals to plus or minus t. It's kind of a weird notation. He says that this is a 2-to-1 homomorphism because the two elements t and minus t of SU2 go to the single pair plus or minus t in SO3. So he said SO3 looks simpler than SU2 because SO3 only has one element, whereas SU2 has two. And in fact, SO3 is a simple group. This is page 33. He says the only non-trivial subgroup of SO3 closed under conjugation is SO3 itself. Did you get that? Now, this notation's a little funny. I mean, what he's really saying is, what is SO3, I guess, is the question. I mean, this is... I mean, when I think SO3, what I'm really thinking, I mean, outside the scope of geometry and other things, I think, well, that's a 3x3 real matrix. Such that R transpose R is equal to the identity, and the determinant of R is equal to 1. So for me, that's what I think of when I think of SO3. You know, how do you actually produce that particular 3x3 matrix from this SU2 matrix? He has not made explicit, but it runs through this argument about the antipodal pairs. It seems like a good homework problem. Make this map explicit. That's either a really good or a really annoying homework problem. I'm not sure which at the moment. Give it a stab. If it takes you more than 10 minutes, stop. Okay. Okay, so this proof that SO3 is simple is not a simple proof. I mean, sorry. I mean, it's very geometric. If you read page 33 and 34, he argues on the basis of specific geometric picture and construction of angles on a sphere, and there's a topological argument built in here. It's I'm still digesting it personally. I read it earlier and I haven't quite come to terms with it yet. I'll think about it some more for next week. But
so he proved that SO3 is simpler than SO2.
No,
than
he
SU2.
He proved SO3 is simple, meaning that it has no non-trivial normal subgroup. And then in the next section, we have that the reflection represents reflection representation of isometries is any isometry of Rn that fixes the origin is a product of at most n reflections in hyperplanes through the origin, which is a wonderful theorem because reflections are so simple. I don't mean that in the technical sense of simple, okay? Sorry. It's somewhat evil that in mathematics we've chosen to make the word simple a technical term. This seems wrong. But we did it. And like complex numbers are actually simpler than real numbers, and yet we call them complex, right? I don't know. It's not right. And then in section 2.5, he uses this technology about reflections and isometries to build up the fact that rotations in R4 can be built from pairs of quaternions. So we had a rotation in the unreal part of the quaternions is induced by conjugation of a particular quaternion, unit quaternion, right? And here he will show that the rotations in R4 are built from pairs of quaternions, and that will ultimately allow him to prove that, eventually he uses that in section 2.7 to show that SO4 is in fact not simple. It's a natural build up to that, as we'll see next week. I'm sorry. But let me just say a word or two about the idea of simple groups. Like the whole discussion about simple groups originally arose from, back in, where did group come from really was Galois. So what Galois was trying to do was understand why can't we solve the quintic. And so what he did was he looked at solutions. He noticed that there's certain patterns between solutions to polynomial equations. In fact, they have a group structure. And he was able to show that if the equation has a solution, then the group has a very particular structure that can be broken down, right? And long story short, if the group that comes from the roots of the polynomial is simple, that way of breaking it down into solvable subgroups, which allow these sort of natural quotients, it breaks, it fails. And so the A5, this particular group of permutations is present in the quintic, the general quintic. And so the presence of this particular simple group in the groups of the Galois groups of quintic polynomials and higher order polynomials means that you just simply cannot break it down into radicals. There cannot be a quadratic type formula, let's say, for quintic and higher. That came from this abstraction that Galois did, to these groups and the study of solvable groups. So simple groups, the study of simple groups goes back to that problem of Galois, and our current study of simple groups is born from that discussion, as he explains in the discussion. And this is that couple pages he has, the insight he has tying the Galois to what Lee did is very useful in terms of a little bit of math history. Anyway, I'll shut up for today. So thanks, guys. All right, I guess you can go to your math meeting if you must. Let's see here.